Hello, Mr. Jones. So this is our first lesson for AP Chemistry, and we'll be doing notes for pages 1 through 4, which I have lined up here. You really can't tell, but I just know because I'm the one that put them there. 1, 2, 3, 4. You'll know quite a bit of this stuff already, and I'm just going to add in the details that weren't covered last year and the spicy bits that you'll see why we don't bother covering it last year. It's better to get that fundamental in 1 year and then we can add on to it this year. So let me jump right in here, but not like that. That's not what I wanted to do. Let's do this. This is better. Okay. All right. Now, as we go through this, feel free, obviously, to pause the video whenever you want, so you can fill things in like this. Likewise, feel free to pause the video and redo a problem. So for example, if we look a little bit lower, here we have a calculation. After I show you how to do this, pause the video once you think you understand it, cover it up. So cover up this entire area so you don't see the work anymore, but you can still see the question, and redo that problem. If you can't redo the problem that I've already done for you, then homework is probably not going to go well. Back to the top. I talked about these things and a few other things in my, what I call good technique video. So hopefully you watch that first. If you haven't, then stop this and go back and watch that one first. And we'll be using these techniques the entire year. Okay. So we're going to start with ionic naming. Now you already know how to do ionic naming, but there's some additional bits. First, make sure you know your polyatomic ions from last year. Most teachers have you learn 8, like phosphate, nitrate, ammonium, and so on. Also, make sure you learn the new polyatomic ions. Now, the new polyatomic ions were in the summer work. Hopefully, you've already looked at that and memorized those. If you haven't, you need to find the summer work, which is on my website. And at minimum, you need to find the list of polyatomic ions and start memorizing those immediately, because it takes a little while. Now, it turns out what most people do is they learn the ions that end in 8 right here, like sulfate. But there are relatives of that ion, and the difference between them is the number of oxygens. Everything else is the same. The charge is the same, the other atom's the same, and it's just you add or you remove an oxygen. So if you know the one that ends in 8, if you add 1 oxygen, the way the naming changes is you put per in front. So if you had nitrate, for example, and you added an oxygen, it would be per nitrate. Back to the regular one. If you remove an oxygen, you change the ending to ite. So nitrate would become nitrite. If you remove another oxygen, you then add hypo in front. And some polyatomic ions have all 4 versions. They all exist in the real world, and some don't. Some only have a couple of the versions in here. You wouldn't necessarily know which ones exist and which ones don't, and don't worry about it. So I have an example right here. You should know that SO4 is sulfate. If you take 1 oxygen off, you now have SO3, same charge, -2, that becomes sulfite. And we'll do a little more practice at the bottom of this page. Next thing, hydrates. You should have studied hydrates in first year chem, and you should have done a lab And just a quick review, a hydrate is when you have something ionic and there's water molecules trapped in it. So in my example here, I have copper sulfate, copper 2 sulfate to be specific, and there are waters trapped in it. Now, when you look at it, doesn't look wet. Like if you had like a sponge filled with water, that's different. These are stuck in there. They're almost like you wouldn't know they were there. And the way we name these is you name this part like normal, copper 2 sulfate, and you do the prefix for 5, penta, and just add the word hydrate. So copper 2 sulfate pentahydrate. They're not a big deal, but it does make sense to review this. Also, there will be a homework problem in your first homework about hydrates, and it can be useful to look back at your hydrate lab from last year. So you get a little, or at least look back at your notes, so it gives you a little bit of a review. Moving on to covalent right here. You're pretty good on the regular molecules. So you need to know your prefixes, just 1 through 10, like mono, di, tri, and so on. And regarding acids, you learned 6 strong acids last year, like hydrochloric and sulfuric, but you didn't learn how to name the other acids, and it's pretty easy if you know your polyatomic ions. And all you do is if you take a polyatomic ion and it becomes an acid by putting a hydrogen with it, you look at the ending. If the polyatomic ion ends in 8, you changing the ending to ic, acid. If the polyatomic ion ends in 8, you change the ending to us, acid. In my head, I think ows, so I spell it correctly. But most people just say us. If there's a per or a hypo with the polyatomic ion, you just keep that. So we'll take a look at an example right here. I have 4 versions of a chlorine oxygen polyatomic ion. The one you should have memorized is right here, chlorate. If you add an oxygen, you get perchlorate. If you remove an oxygen from chlorate, you get chlorite. If you remove another oxygen, you get hypochlorite. And these are just the polyatomic ions. These are not acids. And I made a note here. You might have heard of sodium hypochlorite because that's what's in bleach. So feel free to pause the video, go wherever the laundry stuff is and take a look at the bleach bottle and it'll say it on there. I forget the percentage, but there's a particular percentage of sodium hypochlorite in bleach. Now, if we take these and we look at their acid version, notice they now have a hydrogen. That's the hydrogen that would be given off as it acts as an acid. And notice how the naming works. 8 becomes ic. So perchlorate becomes perchloric, and you add acid. And this one you already knew. This is one of the 6 strong acids, so you should have already had this one memorized from last year, but now you know why it's called that. This one would then be chloric acid. Because this is coming from chlorite, it's chlorous acid. And then this one would be hypochlorous acid. Now, I've got a side note regarding acids that this can cause a bit of confusion sometimes. HCl aqueous, what that means, because this is a strong acid, it means that the hydrogen and the chlorine are separated. They exist like this, as H plus in water and Cl minus in water. That is an acid, and you should know it as hydrochloric acid. HCl gas, because it's not in water, these do not split into ions. They're still bonded covalently, so that is not an acid. You just name it as if it was covalent. Hydrogen chloride, if you said hydrogen monochloride, that'd be fine. And this, like I said, exists bonded as HCl. This will come up a little bit in our second lab. And sometimes this messes students up if they don't see the difference. All right, now on to some math. Something called the limiting reactant is exactly what it says. It is the reactant that limits how far a reaction can go. In other words, it's the thing that runs out. Now, a lot of times when doing things like stoichiometry and balanced reactions and limiting reactant, people like to use the example of a recipe in cooking. And I think the most obvious one would be you're making chocolate chip cookies. Let's say you go into your kitchen, and in your kitchen, you get out all the ingredients, as much as you have, because your goal is to make as many cookies as you can. So you get out the flour, and you get out the sugar, and you get out the chocolate chips, and so on. And all the other things that you might need. I'll just go with these three. If you get out all three of these things and you figure out how many chocolate chip cookies you can make, one of these three ingredients is going to run out first, and you have to stop at that point. So that is your limiting reactant. So let's say that you had a bunch of chocolate chips and a bunch of flour, but you didn't have that much sugar. What would happen in this case is that the sugar, it runs out first, is your limiting reactant. It's limiting how much you can make in this case. So let's take a look at a real example. By the way, you'll notice on this, I've got a little drawing here. That's a little eggmobile. I put that next to things that I want to emphasize. So it's just a corny way of doing it. You can put a star or an arrow or a flower or an eggmobile. So whatever the heck works for you. So looking at the steps here, you have to have a balanced equation. You have to turn grams to moles, unless it's already in moles. Remember, in a balanced reaction, you can always compare everything in moles. That's the main of having a balanced reaction. You can never compare the chemicals in grams because they have different molar masses. Now, once you see the moles of each reactant, sometimes it's obvious. You don't need to do any math at all. And so that's what I said by option A. Just use logic. It's just obvious who's going to run out first, and that's your limiting. Other times it's kind of hard to tell. So option B, take the moles of each reactant, however many there are, and turn them into moles of one of the products. It doesn't matter which product you pick, because whichever reactant limits the production of one product, it will also limit the production of all the other products. So looking at an example here, shrink this down. A reaction is hydrogen, oxygen, forming water. Now in this case, we only have one product, so we can't make a choice. But if there were multiple products, like water and another thing and another thing, it really doesn't matter which one you pick. But what we have to do is we have to compare which of these is going to run out first. So the author of the problem says 3 grams of hydrogen, 8 grams of oxygen. Which one's the limiting reactant? Don't ever tell me the limiting reactant's a product. It's called limiting reactant, and it will always be a reactant. So I took the grams of hydrogen, grams to moles, moles of H2 to moles of H2O. That's my stoichiometry right there. And it gave me 1.49 moles of water. Did the same thing for the 8 grams of oxygen. 8 grams of oxygen, grams to moles, moles of O2, moles H2O. Of course, the 1 and the 2 come from the balanced reaction, and you get 0.500 moles of water. And what you now do is you compare these two things, and you see who made less water. That one's going to run out first. In this case, it's the oxygen. Even though there were more grams, the oxygen ran out first, as you can see here. And so we say oxygen is limiting. The proper term for the hydrogen is that it is excess. What that means is after this reaction is completed and the oxygen is completely used up and there's no more oxygen, and you've made as much water as possible, you're still going to have some H2 left over, and hence that term is excess. Now, I added a question here. How many moles of H2O gets produced? Well, that's based on the limiting reactant. Limiting reactant was the 8 grams of oxygen, and it produced 0.500 moles of water. So the amount of water that gets produced is 0.500 moles of water. Now, often a set of questions will start with a limiting reactant problem like this, and then they'll ask more questions based on that. And often there will be follow-up questions in which you need to use the limiting reactant, like I have here. So based on the last example, how much excess in grams, as opposed to moles, would remain? Now, this is not being specific. It's not saying, oh boy. I'm sure I'll get better at this as we do more of these. It's all upset now. And well, whatever. Let's do this. There we go. When it says how much excess, it really, it should be a little more clear and say how much excess reactant, but you just kind of have to go along with it in this case. You should just know that the excess is the H2. So there are a few different ways to calculate this, and if you have a particular way that you like, there is more than one way. For example, you can start with the 0.5 moles of water, but I recommend always go back to the thing that you know for sure. What you know for sure is that the oxygen is limiting. So take the amount of oxygen, turn it to moles. We want to know, based on that much oxygen, how much hydrogen is going to react. And of course, in the reaction up here, it's 1 to 2. Turn your moles of hydrogen to grams, and you get 1.01 grams of hydrogen. Now at this point, realize that's not the answer. Often students get to this point right here, and they get this, and they're like, oh, I calculated something. I'm done. They don't think about what they just did and whether that is the answer. That's not the amount of hydrogen that's left or in excess. That's how much reacted or was consumed. So what you have to do is go back up here, take the 3 grams of hydrogen, subtract the amount that reacted, which we have here, and then you find that it was 1.99 grams of hydrogen that was in excess. Now, one thing you can do right now that will really help you is, go back for all these weird things I did. Go back here. And don't make random blue lines on your page like I did. Go back to this. Cover this up. Make sure you understand it first. And redo this problem. Make sure you understand it and you get it right. And then do the same thing and redo this problem. And then move on. And that's just going to be some good practice. It'll make sure you understand it. It's one thing watching me explain it already written out, and it's another thing you doing it on your own. And to emphasize how much I want you to do that, I am actually going to stop the video right now, and that'll kind of force you to do something. And then I'll make a part 2 to finish the lesson.